All right, so we're going to continue with section 13.3, and we're on page 844, working exercises. Page 844, we're going to start with number 30, which says, in exercises 29 through 33, find the partial of f sub xy and f sub yx. So, and they give us the function is, well, before I even write down the function, let me just write down what they want because we haven't done this yet. So f sub xy. Now, this is just saying, first find the partial of f with respect to x. Whatever you get there, find the partial of that with respect to y. That's what that notation means. So now there are other notations for this, and I'll write down some of the other notation. This is also the same as, this is what's called a second partial because we're taking two partial derivatives. So we can also use this notation that this is the second partial of f. Now with this notation, we look at whatever we're doing first comes on the right, and I'll rewrite this so that you see why that is. Because I'm going to put two things down here in the denominator, or the lower part of this thing. So this is the second partial of f. First thing we're doing is with respect to x, and then we're doing with respect to y. So the y goes there and the x goes there. And the reason being is because this is the same as this notation. The partial of f with respect to x. So all of those are the same thing. Notationally, this is also equal to some other things, but notationally, those are all the same thing. The partial of f sub xy is you take the partial of f with respect to x first, and then with respect to y. That's the same thing this says. So that's why the notation here is flipped. It's just that we do what's inside of the parentheses here first, and then this is like the operator telling us what to do afterwards. So you do this, and then you do that. Same notation here. You do this with the parentheses on that side, and then you do that. So the parentheses go with wherever the f is, excuse me. So that's why here they're on that side, and here is on the other side of that flip. But luckily for us, that's not really going to matter, because when you all's reading, you'll find out that for our purposes, f sub xy is the same as f sub yx. So it's not really going to matter if you confuse which one you're supposed to do first for any of the problems that we encounter. All right, so now what was our function? Our function for this problem was f of xy equals x squared minus y squared over x squared plus y squared. And notice the derivatives we've been taking just have been relying upon our knots of derivatives from Calculus 1. Nothing else is necessary, so we haven't been using any new differentiation techniques that were learned in this course. So now we want f sub xy, but to find f sub xy, first we have to find f sub x. And then after that, we're going to find the partial derivative of f sub x with respect to y. So first, let's just start with f sub x. All right, so partial of this with respect to x, we'll just use the quotient rule. So we get 2x for the numerator, and then times x squared plus y squared, and then minus, we get, now remember, we're only taking partials with respect to x now. So now we're taking the derivative of the denominator, but just with respect to x. So 2x times the numerator, which is x squared minus y squared, all of that over the quantity x squared plus y squared squared. And to simplify, let's see, we're going to get 2x cubed plus 2xy squared minus 2x cubed plus 2xy squared. Okay, so it does simplify. So we get this equals, let me just write it down, 2x cubed plus 2xy y squared minus 2x cubed plus 2xy squared all over the quantity x squared plus y squared. So these two terms cancel, and this is just equal to 4x. And so for these, now I know I've said a lot, don't simplify if you don't have to. This is where you absolutely will want to simplify because you don't want your derivative to become more complicated. And I mean, you all found that out in previous questions or problems as well, especially like when you're working with the unit tangent vector and unit normal vector. You always want to simplify things as much as you can to make your work easier because of all the successive steps. So now we have 4xy squared over x squared plus y squared, quantity squared. Now, keep in mind here, we were asked for f sub xy. There is such a thing as f sub xx, where we will be taking the partial with respect to x again, but that's not what we were asked to do. We were asked to take the partial with respect to partial of this thing with respect to y. So f sub xy, which is what we were asked for, is we're going to take our f sub x, our function, and this function, we're going to take its partial with respect to y. So now, there we get partial of this with respect to y. We have to use the quotient rule. I mean, we don't have to use the quotient rule, but I'll use the quotient rule again. So we're going to get 8xy from the numerator, and then times the denominator stays the same, x squared plus y squared, and then minus, taking the derivative of the denominator. Remember, we're taking, oh, did I do this with respect? Yeah, I did. Remember, we're doing with respect to y. So the 2 comes out, inside stays the same. I don't think this is going to fit on my page. Sorry about that. Negative 2 times the quantity x squared plus y squared, and then that will be raised to the first power, and then times the derivative of the inside with respect to y is 2y, and then times my numerator. This is a tight squeeze for me. 4xy squared, 4xy squared. Sorry about that I had to write that so small. So this was minus the derivative of the denominator with respect to y. So the 2 comes out front, inside stays the same. Derivative of the inside with respect to y is 2y, and then times the denominator stays the same. And this is all over x squared plus y squared to the 4th. Now at this point, you don't have to do anything. I would not simplify that. I mean, you're welcome to, but that's one of those times where you're running a risk there. You can just leave that as is. And it might simplify nicely. I don't know, but there's no need, so you can just leave that as it is. All right, next is, actually for sake of time, what I'll do is if we have some more time at the end, I'll come back and I'll do the other part. But for now, I'm going to leave that to you to try. F sub yx, and you should have the exact same thing that we got here when you do f sub yx. So check that one against what we got here. Actually, if it requires you to simplify, if you can't immediately see it, don't worry about trying to check that the two are actually equivalent to one another. Keep in mind, though, that you have to find f sub y first. So you still have a 2-step process just like we had here. All right, so now I'm going to go on to number 40. I want to make sure we see this problem because it's one of the applied problems. So number 40 says, I have space here. I think I do. So number 40 says, find symmetric equations for the line that lies in the plane x equals 2 and is tangent to the intersection of the plane and the cone z equals the square root of x squared plus y squared at the point 2, 2 root 3, 4. All right, so let's just do a little or actually what I'm going to do is I'm going to use our sketch from our first 13.3 video to, because I explained there what an application is, or what the physical interpretation is of the partial derivative. So I'm going to explain this problem in terms of this picture, although this picture is not a cone, but we're going to pretend that we have, or actually for us, it's going to be just this picture. So let me put that off to the side. And now I'm going to read the question again, and I'm going to point out what they're saying in that question in terms of this picture, pretending that this thing is the cone, although it's not. All right, so it says find symmetric equations for the line that lies in the plane x equals 2. So pretend I slice through this thing at x equals 2. So it's going to be a line that lies in that plane x equals 2. So this dotted line, and then that curve right there, that's the plane we're stuck at, x equals 2. And it's tangent to the intersection of the plane. So tangent to the intersection of this plane. So my plane would slice through there, and I'm just going to intersect the plane, and for us, they're saying the cone. So this region that surface we initially had drawn, that's the cone. And then we take that cone, we slice through it with the plane, and then we look at the line of intersection, or the curve of intersection, of the cone. Remember, this is not actually a cone, but theirs is a cone. The cone and the plane will be that curve right there. They want the tangent line to that curve at some point. So this point right here, or in that problem, would be, well, first, this surface right here would be the z equals the square root of x squared plus y squared. And then the point, this would be the point 2, 2 root 3, 4. So they're asking us to find the equation of this tangent line right here, is what they're asking. Now, it may seem convoluted, but that's basically the only way to explain that without drawing a picture for you and them saying it, which they're not going to do. So you just have to understand what is going on when you talk about partials. Now, the fact they told us x equals 2 tells us that we are going to use f sub y because x is remaining constant. So now let's go ahead and approach the problem. One other thing while I have this picture up. Now, I said f sub y is the slope of the tangent line in the y direction. And that's what we're doing. We're looking at the rate of change in the y direction, going from, as we look in the page, from left to right. Well, for us, we're going to go in the positive direction from left to right, because this is the positive y-axis. Now, your slope is, f sub y is your slope. Now, your slope still is your change in, or your rise over run. So for us, if you want to, you can go back and put this on your picture from the previous video. So our rise is our change in z, over our run is our change in y when we're doing this. So is for this, in this particular scenario, our f sub y is going to be negative at that point, because we're going to go down and then over to the right. So over your change in y, this is what f sub y is. What f sub y? Well, this is f sub y. So f sub y is that. Now, when we want, we're trying to find the equation of a line. So we need a vector L that is parallel to the line. So what we're going to use is the vector that is given by this, the slope basically, or the slope of that line. So think of it this way. How far do we go over in the x direction for the slope of this line? The x direction is stuck. We don't go left or right at all, or in or out, I guess you would say, at all. We don't come out of the page. We don't go in the page. So that tells us for our vector L, the x component is going to be 0. Now, what about in the y direction? We can look at this as our slope if we're stuck in this plane. So you would say in the y direction, well, we're going 1 unit in the y direction because that's your change in y. Or look at this as this, over 1. Right? Because change in z over change in y is the same as f sub y over 1. So our change in the y direction is 1. Then our change in the z direction is f sub y. So that's how we determine our vector L. So now let's go back to the particulars of our problem, and I'll jot down some of those things I just discussed there. So first, since X is held constant. We need to use f sub y or z sub y in this case, because they gave us our function in terms of z, or z sub y in this case. The vector L parallel to the line will then be L equals, so 0 in the x direction. And this vector L that I'm going to give you is not specific to this problem. I'm going to give you a general vector that if you encounter a problem like this where your x is being held constant, this would be your vector L that's parallel to your line. Y, I'm going to skip y for a second just so we can see. So the change in z over the rise over run, let's look at it that way, which is the change in z over the change in y. What is the change in z going to be? Because we're just looking at a vector, and that's how we determine vectors is, okay, how far do we go in the x direction? How far do we go in the y direction? How far do we go in the z direction? The rise over run is change in z. Change in z is f sub y or z sub y. And then your run is just 1. The change in y is 1. So for every time you go up or down f sub y, you're going to go to the right 1, is what that says. So this is going to be your vector L that's parallel to your line. So now you just need to find f sub y or z sub y in our case. So our z that we were given was, somewhere is it? Square root of x squared plus y squared. So z is equal to the square root of x squared plus y squared. And now we need z sub y. So that's going to be 1/2 times the quantity x squared plus y squared to the negative 1/2 times the derivative of this inside with respect to y. So times 2y. So now, after we finish this problem, see if you can write this exact same thing down, but in terms of y. Since y is held, or if y is held constant, we need to use f sub x, and then what would this vector be? Just remember your y is held constant, so yeah, you want to move in the y direction also. That's going to be 0 in that scenario, is because you're not moving in the y direction. All right, so now we have this to put in that vector, but they gave us a point that we need to consider. So our point P naught was 2 root 3, 4. 2, 2 root 3, and then 4. So now we have the vector L and we have the point, but we are going to have to put this point into here as well. So I'll quickly do that with our vector L, and then I'll let you all put the symmetric equations together. So L is going to be equal to 0, 1. And now I'm taking this point and putting it in there, and that'll give us, then you'll have your actual point in your actual vector that you're going to use to put together your symmetric equations. So we're going to have 1/2 x squared plus y squared. It's going to simplify nicely. Let me just write it out though. 1/2 4 plus 4 times a 3, 12 to the negative 1/2 times 2y, so 4 root 3. Close that. So all I did was plug this point into that to get with my, remember z sub y and f sub y, there z and f can be used interchangeably, so those are the same thing. So now you would of course simplify, because that will simplify nicely. So you would simplify this, you would get that would give you your vector L, And then from there, you're going to take that vector L along with this point and use the symmetric equations of a line and come up with the symmetric equations of that line. All right, so we'll conclude 13.3 there, and in our next video, we'll start section 13.4.